Now in these next two sections, we're going to talk about what integral really is. So integral or antiderivative is really trying to find the area under the curve. And when we say under the curve, we mean the function f of x, and also we mean the area between the curve and x-axis. And then I'll show you what that means. All right, and then so to do that, if it is a very specific shape, so for example, let's say the curve looks like this, and you're trying to find, let's say, the area between here and here. So when we say under the curve, we mean this area under the curve, but enclosed between the curve and the x-axis. Let's say you're trying to find the area here. Well, that's a known shape. That's just a trapezoid, and you can find it, the area very easily. But if you cannot find an area very easily because that shape is not a recognized shape, then what you have to do is approximate. So when we approximate, we use this idea called, or this method called Riemann sum. So we're summing up something, and that something is rectangles. So we're going to create a lot of rectangles to help us approximate the area. For example, let's say there is this area that we're trying to find between the curve square root x and the x-axis, and then we're trying to do that from 1 to 5. All right, so you can see that this curve is not a recognizable shape, so no matter how I do it, so we're doing this from 1 to 5, so we're trying to find this area. I can't really find this area as it is. I know this part is 4 units because I can see that's 4 squares, but other than that, there's nothing I can do. Let's try to do this systematically using this thing called a Riemann sum. So here's how Riemann sum works. We're going to break this up into equal distance with however many intervals we want. So this question says, please use 4 intervals. So I'm going to break this up from 1 to 5 using 4 intervals. So that's going to give me each interval being a size of 1 in width. How can you find the width of this interval really quickly? Well, let's say the width, so this triangle means delta, delta means change. So the change in x, meaning how wide x is going to be your end point minus the beginning point. So this being b, this being a, divided by however many interval, which is 4, that's, we're going to call that n, however many interval you're trying to divide it into. So in this case, we're stopping at 5, starting at 1, and then we are trying to separate into 4 intervals, so therefore each width is 1 unit long. Okay, well, we're trying to create some triangles, and then this triangle, rectangle, and then this rectangle is going to be approximated using 4 different methods. Well, to be more specific, the rectangle is by 3 method, and then the last one, trapezoid, is the trapezoid. So the left Riemann sum means we're going to use the left-hand side of the interval to create this rectangle. So for example, in the Riemann sum, left Riemann sum, we're going to use the left-hand side. The left-hand side of the rectangle is this side. That hits the curve, and then we draw a straight line across. That's going to create our first rectangle. And then so same thing from between 2 to 3. The 2 is the left-hand side, so we take the left-hand side hitting the curve, draw straight to the right, and then that creates another rectangle. Same thing here, 3 to 4, take the left-hand side, which is 3, that hits the curve right here, draw the line over, so this creates the rectangle, and then this is the last one. So 4 rectangles there. So this would be called the left Riemann sum. If we're going to do the right Riemann sum, we're doing the same thing, except this time we take it from the right. So I'm going to do this in a different color so you can see it better. Right Riemann sum, so between 1 and 2, we're going to take the number from the right, so 2, that hits the curve here, and then draw a line over. That's my rectangle, and then do it Same thing here, here, and then here. So this is called the right Riemann sum. All right, the next one is called the midpoint formula. So the midpoint formula is using the middle. So between 1 and 2, we're going to start at 1.5. That goes up to where the curve is, draw a line through both sides. That creates the rectangle. All right, so same thing, 2 to 3. So we're going to start from 2.5 or at 2.5. Wherever it hits the curve, draw a line, creates the rectangle. So same thing with 3.5, 4.5. Now with a trapezoid is pretty simple. So what you're going to do is just create a trapezoid using the two endpoints like this. Okay. Now, eventually the question we're going to ask ourselves is, which is the better approximation? And which is the better approximation for this case? And then also, which method is going to overestimate and underestimate, and how do you know, and is it always true, or is it based on a curve? So, we're going to answer all those questions. All right, so, but before all that, let's go ahead and kind of talk about how we're going to find those areas. So first, we're going to take that width, and then we're going to multiply by a height. Well, the height is going to depend on where you hit the curve, right? So then that's going to be wherever the function is at that x value. And then this I means the iteration of x. So then the area is going to be width times height, or width times height. So the width is always the same, and then we have the first height plus the second height plus the third height, and so on until we add up all of the rectangles. All right, so let's go ahead and look at the first one, left Riemann sum. So what we're going to do is take the width times the height. So what we can do is you can create a table if this is very confusing for you. So you know the width, let's just say width is always 1 in this case, and then the height is going to depend on f of x. So again, if this is very confusing, you can also write x here. So I'm taking the left-hand side of each interval. So between 1 and 2, I'm going to take the left-hand side. Between 2 and 3, I'm going to take the left-hand side. 3 to 4, left-hand side. 4 to 5, left-hand side. There is no 5 to 6, so there's no 5. So be careful with that. The width for all of them are the same. They're all 1s. The height is going to depend on x. Well, the height is based on the function square root x. So we're just taking square root 1, square root 2, square root 3, square root 4. Well, this is 1, this is 2. The other ones you have to use the calculator. All right, so then the area is basically width times height. That's going to give you area. So this is 1, square root 2, square root 3, and then 2. And then the total area is when you add them all together, which in this case is 6.146. All right. In the same idea, you're going to do the right Riemann sum. So if you like to have a chart all the time, you can do that. Right Riemann sum, we're going to start at 2, 2, 3, 4, 5. All right, go ahead and give this a try and find the total area. The answer is 7.382. All right, let's try the midpoint. So same idea. It's a little bit harder to do because you're finding the middle. So between 1 and 2, that's 1.5. 2 and 3, 2.5, 3.5, 4.5. When you put it into the function, make sure you put the actual x value. All right, so same thing on this one. Find the area. The answer is 6.798. All right, last one, trapezoids. Trapezoid is just, whether you remember the trapezoid formula. All right, so trapezoid, all right. What you do is, let's say your trapezoid looks like this. You have, let's call this the height, and this is base 1, base 2. Then the area of a trapezoid is equal to 1/2 h base 1 plus base 2. So in this case, what you're going to do, it might be easier if you don't draw a table and you just find each area. So you're going to take 1/2. The height is basically the width, so that's always 1. Base 1 and base 2, that's the first trapezoid, plus the second one. 1/2 height, base 1, base 2. Okay, okay, plus 1/2 times height, base 1, base 2. And then the last one, 1/2 times 1, base 1, plus base 2. Okay, you can see that if you factor some of these out, it's much easier if you do it the other way, which you can see here, this 1/2 and 1 are repeating, right? If I were to factor all that out, I would get a square root 1 plus square root 2 plus square root 2 plus square root 3 plus square root 3 plus square root 4 plus square root 4 and plus square root 5. So then you can actually further simplify this formula. And then you can see that it's basically 2 of these, 2 of these, 2 of these, and then the 2 endpoints, there are only 1 of each. So if you want to remember this formula for later and you're trying to calculate just a nice trapezoid later, you can just say it's 1/2 h times base 1 plus 2 of base 2 plus 2 of base 3 plus however many you have, and then you have the last one as is. Okay, anyways, let's go ahead and calculate the actual area, total area using trapezoid. So go ahead and calculate it, come back and check your answer. Okay, the answer is 6.764. All right, the question now is which one is the closest? Well, I'm going to probably say trapezoid, right? Because trapezoid pretty much looks like that shape. Now, if we're talking about left and right, if we have to compare left and right, which one's going to overestimate and which one's going to underestimate? It's pretty clear to see that left hand is going to underestimate, and the right hand is going to overestimate. Why is that? Because of the shape, right? Is it because this shape is increasing, or is it because the shape is concave down? So this is actually because it is increasing. So underestimate because f of x is increasing rather than concavity, because you can see that even if it is concave up like this, the left hand side is still going to estimate because the left hand value is always going to be smaller than the right hand value. Therefore, it's always going to underestimate. And then so same thing, right hand side is always going to overestimate in this case because this function is increasing. Now we're going to take this shape and then we're going to kind of think about what happens if I were to increase the amount of areas. So same thing, we're going to take it from 1 to 5. This time, instead of 4 intervals, let's increase it to 8. So I'm going to half this. And let's say I draw some rectangles again. Let's draw it from the left. Would this be a better estimate than the previous one? Of course it would. Let's say we double that. We double it to 16. And then I draw the left-hand one. Would this be a better estimate? Of course, much better than the 8 or a lot better than the 4 intervals. So what if I increase it infinitely to so many rectangles that the width is infinitesimally small? So how do we write this as in I am increasing the amount of intervals to infinity? And then I'm trying to figure out what area would approach. So does that sound familiar? So we are basically asking a question of limit. So what we're saying is we're trying to add up the area, and I'm increasing the amount of area to an infinitely many amount of area. So basically, we're trying to take the width times the height, and there are many, many, many of these little rectangles. So the first rectangle plus the second rectangle plus many, many more forever. Sorry about that. And then I can kind of change this by taking the delta x out of there. Just rewriting this. And then I'm basically just saying I'm adding up all of these rectangles. So another way to write that is just saying the sum of the height times the width. The width is consistent, so we don't need an I on it. And then we're saying from the first rectangle or first height to n. That's if you have a finite sum of rectangles, right? What if you're going to do this infinitely? Then you would say it's the limit as n goes to infinity of this same sum. Now, what happens if you do take it to infinity? Then this becomes the integral, the smoothed curve. So instead of having all these jagged rectangles adding up together, you're just having a smooth curve finding the area under the curve. So then we would just say f of x dx. So here's how the two matches. This part is the f of x part. Delta x is the dx part. So it's this basically means width times height. Now we're going to practice rewriting this problem in terms of this limit notation. And then we're also going to practice writing this problem in integral notation. So let's look at this problem again. So this is the same problem we were trying to solve before. So let's say f of x is square root x. We're trying to find the area under the curve between x equals 1 to x equals 5. And this time we don't have a limit on how many rectangles we're going to use. We're just going to use infinitely many rectangles. So we're first going to write it in the summation notation. So this is called summation notation if you don't recall that. And this is the integral notation. All right, to write it in the summation notation, we need to first figure out what delta x is. Remember, delta x is the end minus the beginning over however many there are. Well, this time we have so same thing as before, 5 minus 1, but we have infinitely amount of n, so I'm just going to leave it as n. So this is 4 over n. All right, now let's talk about f of x, because that's, we figured this part out. Now we're going to figure out this part. So f of x, it's an index, right? We're trying to, figure out the height at every x value. So how do you figure out the height at every x value? Well, the first one is going to be 1 because we're starting at 1. The next one is going to be however much we want to move over on the delta x, right? So basically we start at the first one and then we move over delta x. And then we keep adding delta x over and over and over until we get to the last point, which is 5. Therefore, when we write this, we're writing the first number plus delta x. So in this case, since the function is square root x, we're going to write square root x, and then from the first number, which is 1, plus, and then delta x. Delta x is 4 over n, but we're going to keep adding 4 over n every time we move over one iteration. So we're going to put an I there. And then so finally, if we put that together, we're going to write limit as n goes to infinity of the summation notation from starting with I equals 1, so that's when you only have one triangle or at the first triangle, to nth triangle, rectangle, I keep saying a triangle, of the function. The function is square root 1 plus 4 over n I. I means this is however many iteration times 4 over n, which is the width. Okay, let's go ahead and practice this. Okay, so let's try it for this one. So this is the integral from 3 to 8 of x squared dx. So from here, in order to write the limit notation, we need a few things. We need to know delta x, we need to know a, b, and then f of x. We know that delta x is going to be b minus a over n. And then what number is a and b? Well, it's starting at 3, ending up at 8. So that's 8 minus 3 over n. We keep it as n because we have infinite amount of rectangles. So this is 5 over n. We know that the function in this case is x squared. We're going to take the first number, which is 3, plus the width of the rectangle, which is 5 over n, and then we have this iteration every time we add another one, and this is the function square, so x squared. Now we're writing the limit notation, so limit as n goes to infinity of the sum of the first rectangle to the nth rectangle of the function times the width. All right, now we're going to go backwards. So we are going to look at the summation notation, and we're going to turn it into an integral notation. So in order to have an integral notation, what we're going to need is we need to know delta x. So then from delta x, we can figure out a, b, and then the function itself. So this is a little bit trickier. Here's kind of my hint on it. So what you're going to do is when you look at the limit notation, you're looking for the part that's repeating, because that part that's repeating is most likely the delta x. And this question, you can see that it's very clear. It's 2 over n, especially since there's an I there, right? So 2 over n is my delta x. All right, the next thing I'm going to try to figure out is we know that delta x is b minus a over n, so I need to figure out what a and b are. The only thing I can tell from this summation notation is a. A is going to be my first number that I'm adding over, so I know that a is 1. And then from here, what I'm going to do is solve for b. All right, so here's what you do. You see that 2 is equal to b minus a, where a is 1. So you're going to solve that. So 2 is equal to b minus a is 1, so b is equal to 3. Next, you're going to kind of decipher what you think the function would be. So we know this is delta x. This must be the function. The function has a plus delta. So then the function must be natural log x. All right, we got everything. So we're going to write the integral. So it's the integral from 1 to 3 of natural log x dx. So let's go ahead and practice just one here. This one should be pretty easy. All right, go ahead and write down what you think the definite integral is. All right, we can see that delta x is equal to 5 over n. A is 2, b is, this is b minus 2 over n, therefore b must be 7. And from all that, we can decipher that f of x must be natural log x. Therefore, this is the integral from 2 to 7 of natural log x dx. All right, let's just do one last one for good measures. This one, just find the definite integral again, and then come back and check your answer. All right, the answer is integral from 0 to pi of cosine x dx. All right, so a quick note. We talked about how area integral means the area under the curve, between the curve and the x-axis. So let's say we're trying to find the area or the integral between here to here, then we're talking about the area. Maybe I should change this color. We're trying to find the area here because that's between the curve and the x-axis, and then here the curve and the x-axis, and then curve and the x-axis. Okay, so it's not a forever below, just between the x-axis. Now what happens is this area actually has a sign to it. If it's above the x-axis, that is positive. If it's below, it's negative. So please keep that in mind. All right, so then let's go ahead and practice one. So this one looks very tricky, but it's actually not that bad. So this says, what is the value of the integral between -1 to 4 of this function? So remember, integral means area under the curve. So it's just asking what is the area under the curve between -1 to 4 of this function being this graph. So it's asking for the area under the curve between here and here. So this part is positive area because it's above, and then this part is negative area because it's below. So since these are very defined shape, you're just going to find the area and then add them together. So for example, this first part, that's a triangle, and then this is a rectangle plus a triangle, and then subtract a triangle and a square. All right, so go ahead and do that and then figure out what the answer is. All right, the answer is 2.5.